two-sided test. So our example from Monday was about a one-sided test. This one is going to be about a two-sided test. In a two-sided test, that's when your alternative hypothesis is that P does not equal the claimed value. So we don't know what it is. We don't know if it's bigger or smaller. We just think that it's different than what the claim is. And so the p-value in these kind of tests is going to be the probability of getting a sample as extreme or more extreme in either direction from the claimed proportion as our sample proportion. Which is kind of weird because we only take one sample. So if we're only taking one sample, how are we going to get two different directions that it could have gone in? So I'm going to kind of show you guys through a picture here how this kind of works. So you have a claimed distribution. Here's my claimed distribution. My hypothesis value is in the middle. That's the mean of this distribution. And we say, okay, this is the claim. Now we're going to go out and take a sample to see if we belong on this claim distribution or not. So we go out and we get a sample. How many samples do we generally take for a one proportion Z test? One sample. If I only take one sample, is there a way that I can be both above and below the claimed value? No. I'm only going to be one way. So let's say for funsies that I get a p hat value that's below the claimed value. And I find the probability of being as extreme or more extreme than that particular value. That looks like a one-sided test. But what I do in a two-sided test is I say, okay, this was a certain distance. It's going to end up giving me a negative Z test statistic because it's below. I say, you know what? I got this particular sample, but I would have been just as happy to get the complementary side and included that as evidence. So I basically go the other direction in the positive Z, and I find that is obviously going to be the same exact area. This upper area is going to be the same as this area, okay? Because I would have been just as happy to get my sample on that side of the claimed value, okay? So that's how these two-sided tests go. Now, does that picture look anything like what you've ever seen in the past? Maybe last unit? Foreshadowing? Possibly. So this kind of looks like when we were drawing confidence intervals and we were looking at the middle percentage. This kind of looks like that. So keep that in mind for later. Now, this could have happened backwards. It could have happened that I took my sample and got my sample on the upper side. And again, I would have been very happy to get it on the lower side at that same distance. These two halves of the p-value are going to be symmetric. Here's the good news, you guys. Great news. You guys ready for great news? Yep. Here's great news. Your calculator goes ahead and gets the total p-value. You don't have to even remember to double it or any of that kind of stuff. It automatically gives it to you. Cool? Okay, cool. All right, so with that being said, let's jump into our example. Yes, ladies and gentlemen, we're already on the back side of the first page. Woo! According to the Centers for Disease Control and Prevention website, 68% of high school students have never smoked a cigarette. That doesn't include vapes, but whatever. Olivia and Macy wondered whether this national result holds true at McKinney-Boyd High School. They surveyed a random sample of 150 students from McKinney-Boyd High School and found that 90 say that they have never smoked a cigarette. Is there convincing evidence that the CDC's claim does not hold true at McKinney-Boyd High School? Guess what? 4-step process. What are the 4 steps of the 4-step process? State, plan, do, conclude. State, plan, do, conclude. State, plan, do, and conclude. God bless you, everyone. All right, cool. Go back, Miss Lakey. There we go. All right. State, plan, do, conclude. Let's state. Do you guys remember how to start the state statement?
But there are napkins.
We will test. We will test at alpha equals. Oh no, you guys, there's no alpha. Whatever shall we do?
0.05.
Ah, yes. We're going to use 0.05 if we are not given an alpha. 5% is kind of our go-to. All right, our null hypothesis is that P is equal to the national average of 0.68. The alternative. Now, it just says that Olivia and Macy wonder whether this national result is true here. And then it says, is there convincing evidence that the CDC claim does not hold true here? So it's kind of like we're kind of wondering, is it 68 or is it not 68? So what would be our alternative hypothesis?
Not equal.
Yeah, P does not equal 0.68. Also, we're doing two-sided today, so all right, there we go. P equals the true proportion of McKinney-Boyd High School students who have never smoked. Nice. State. Done. Cool. After we state, what do we do?
Plan.
Plan. Very good. We're going to plan. So we're going to check our conditions. Random. We have ourselves an SRS of 150 MBHS students. We have an SRS of 150 MBHS students. We're going to check that 10% condition. 10 times the sample size has to be less than the population. 10 times 150 is less than the population of MBHS students. 2,900.
Sorry, honey.
Yes, if we had
That's a lot of
29,000
people.
students, I would be done. I would be out. No way.
We're not
I remember from last
Right.
problem.
Yes, good memory. All right, and now normal. We're going to check our normal condition. Remember, for our normal condition, if we are given a claimed value, we should use that to check our normal condition. So we're going to use n times the claimed value of P naught. So 150 times 0.68. 150 times 0.68. Obviously, guys, I can tell you, and you are probably smart enough to see that that is going to be bigger than 10. Yes, it is. It's more than half of it, so okay, good. But what is it? What is 68% of 150? 102. Okay, that is clearly bigger than 10, so we're good that way. That's our number of successes that we should expect. And then our n times 1 minus the complement here, that also needs to be bigger than 10. So we're looking for 32% of 150. Again, I just remind you guys, if 102 was the number of successes out of 150, then what would be the number of failures, or the remainder or complement of this would be?
48.
48. Perfect. You can use your calculator, it's fine. I'm just trying to help you see how that should go together. So again, you guys, we have 3 conditions and all 3 of them pass. We know that P hat is a good estimation for our sample. We know that we have good variability, and we know we have a normal distribution where Z can be used. Are you ready to do the do?
Yeah.
Let's do it. State, plan, do. So for do, we just need to mention what the name is of the test that we're going to use. We're going to do a 1-prop Z test. Now, this is where your brain has to work. Do you remember where to go in the calculator to do this?
Stat test.
Stat test, and this one is number 5. Stat test 5 When you get there, you should see P naught, X, N, and proportion. All right, P naught. What is the value of the claimed distribution? 0.68. X. X is our number in our sample that has the quality or characteristic that we're looking at. It's the number of successes. And in our sample, this would be how many of the sample size said that they have not ever smoked. 90. Then we've got our sample size of 150. And then for the proportion, remember, this is your sign of your alternative hypothesis. So you're going to want to select that first one, that P does not equal P naught, the claimed value. P naught is the claimed value. When you plug all this in, and you can, again, hit calculator draw, that's going to be your call. If you do draw, I will tell you on this one, you'll see both sides shaded because it's a two-sided test. So you will actually get to see both sides shaded if you do draw. All right, you should get a z-test statistic and a p-value. What is the z-test statistic that you are getting? Negative 2.1. So what does that mean? That means that our sample was 2.1 standard units below the 68%. Our sample was 2.1 standard units below the 68%. That means our sample showed that less than 68% of students at McKinney-Boyd High School have never smoked. Do you hear that? So do we have more people who have smoked or less people who have smoked from the national average? More. Okay. All right, cool. All right, what's the p-value that you guys got?
0.036.
Perfect. Oh, is it 3.7?
No.
It's 3.6? Oh, it's fine. It doesn't matter. All right, cool. Time to conclude. All righty. P-value is 0.036. How is that related to the alpha that we use for this problem?
It's below. It's less than
That is less than the alpha of 0.05. And what happens when the p-value is lower than the alpha?
Reject that null hypothesis.
That's right. We rejected that null hypothesis, you guys. And here's why. It's because there is convincing evidence that P does not equal 0.68 at McKinney-Boyd High School. We have convincing evidence of the alternative hypothesis being true. We have convincing evidence that our P here at McKinney-Boyd High School is not equal to 0.68. Now, what is our suspicion? Is it that it's bigger or smaller?
Bigger.
Our suspicion here is that the proportion that have said that they have never smoked, remember that's what that P is that they've never smoked, is that it's less than, because we have a negative Z, okay? So it looks like our proportion's actually less than. I would have taken that it was more than, but it looks like maybe it's less than. Is there any way for us to find out what it is? If it's less than, what is it? Is it a lot less than or a little less than? We'll come back to that. Because of the fact that we have rejected the null hypothesis, what kind of error might we have made? Right, a type 1. So, since we rejected the null hypothesis, may have made a type 1 error. So what does that mean happened in context of our problem? That means we said P does not equal 0.68, but it really does. So that means we said that our proportion here at Boyd is different than the national averages, but it's not. It's the same. So again, this leads me to the question. if that's true, if R proportion at Boyd is not equal to 0.68, well then what is it? So there's something very special about a two-sided hypothesis test. And it goes back to that picture that we saw at the beginning, where you've got a p-value that is actually on both sides, and how that kind of looks like a picture that we've seen in last unit, of a confidence interval. So a two-sided hypothesis test matches with a confidence interval. So we're going to talk about how they go together. And then you guys, one of you, I know, at least one of you is going to be mad. All right, cool. So,
I will be mad.
yeah, okay. You get to be the token mad lady, okay? All right, I'll tell you, I'll cue you when it's time. All right, the result of a significance test is just to reject the claim or to fail to reject the claim. So if we're rejecting the claimed value, it sometimes makes us wonder, well, if it's not that, then what is it? So there is a link between, now this is very important, you guys. There is a link between confidence intervals and two-sided test. There is no link between confidence intervals and a one-sided test where you think that P is greater than or less than the claimed value. They don't go together. This only works with a two-sided not equal to alternative hypothesis. All right, so here it is. The 95% confidence interval is going to give us an approximate range of claimed values that would be true, or population values that would be true, at an alpha of 0.05 significance level. Anybody notice anything about those two numbers? Yeah. So the 95% confidence interval totally corresponds to a 5% significance level for a hypothesis test. So just to make sure we're all on the same page here, if I have my confidence level for a confidence interval, and then I have my alpha for a hypothesis test, again, this is only for two-sided. Obviously, we just saw that 95% confidence level corresponds to a 5% alpha. One of the other confidence levels that we used quite a bit was 90%. If I have a 90% confidence level, what hypothesis test alpha would that correspond to? Yeah, 10%, 0.1. These just match up. And then what about if I go the other way? If I have an alpha value of 0.01, what would be the corresponding confidence level that I could use for the confidence interval? 99%. See how that works? Easy, right? We are going to find and interpret the corresponding confidence intervals for this problem that we just talked about, the non-smokers at McKinney Boyd High School. And we're going to do 95% confidence level because of the fact that we used alpha of 0.05. So everybody go ahead and go there. Stat test A. Stat test A. Now, Abigail already saw the magic. What do you guys notice about X and N? It's already there.
Because we plugged it in the other one.
Because it was in the other one.
Wow.
Because they correspond.
Because they correspond to one another. Isn't that fun? Yeah, it's great. Now, I do want you guys to know this. You guys never put alpha in your calculator, right? You only write it on the paper. So the 95% that's in your calculator, that's just the default. So don't assume that that's always going to be right. The 95% might have to be changed in the future if you do something different. When you hit calculate, I'm going to give you guys a hint. Don't be in a hurry. Hit calculate one time, because if you hit enter again, it disappears. So you just want to hit enter one time. Don't be doing, a whole bunch of enters, okay? All right, you guys. Do you see the interval?
Yeah.
Do you hate me? Yeah. A little? All right. All right. Point. What is the interval? Point what? 0.5216 to 0.6784. Okay. We need to interpret that interval. You guys remember your sentence? We are
Oh, right.
95% confident that the interval, oh, this brings back good memories, that the interval from 0.5216 to 0.6784 captures the true proportion of MBHS students who have never smoked. So I do want to go ahead and let you guys know that in the future, going forward, when we do confidence intervals again, because they are going to come back again when we do means, you guys will not have to hand calculate them anymore. I will let you use the calculator in the future. Yes. Yes, ma'am? All right, so our final question here is, does our interval lead to the same conclusion as the hypothesis test? So remember, in our hypothesis test, we rejected 68% here at McKinney-Boyd High School. We rejected it and said that it's not equal to 68%. Here's our interval. We believe that the true value is in this interval. So does this interval match up to the fact that we have rejected the null hypothesis of 68%? Yeah, how come?
It's not 68.
Yeah, exactly. So since 68, which was the claimed value, is not in the interval, we would want to reject 68%. Okay? So since 0.68 is not in the interval, we would reject it. We would reject it, and we did. So these two match up. Yes? So if I look at this particular interval, it's from 52 to 67, and so 68 is just slightly bigger. Now, are we a lot lower here? No, it was close, but it is lower. Okay, so this is our possible true values at McKinney-Boyd High School for the proportion that have never smoked. And it does, in fact, match up to what we concluded for our null hypothesis, or for our hypothesis test. Questions, comments, concerns? No. All right. What is the probability of a type 1 error? What is the probability of a type 1 error? That's alpha, absolutely. And what does that mean you did? That means you rejected the null hypothesis incorrectly. You made an error, and you made a type 1 error. That's the rejection. That is the probability of making a type 1 error is alpha, and that is that you reject the null hypothesis incorrectly. What is the probability of a type 2 error?
Yeah.
Remember, alpha is the first letter of the Greek alphabet. Beta is the second letter of the Greek alphabet. This is when we fail to reject the null hypothesis incorrectly. Again, this is an error, so we did something wrong. We did not reject the null hypothesis, but we should have. We failed to reject the null hypothesis, but we should have. So these are our probabilities of making errors. Now I'm going to give you the probability of doing something right. So the probability of rejecting the null hypothesis correctly is called power. power. The probability of rejecting the null hypothesis correctly is called power. Do you guys want to be correct when you make a decision? Most of the time, yes. Usually when you guys make a decision, you want to be right. So do you think you want your power to be high or low? You want high power. You want power to be really high. Now, power is very special to beta. They are complementary of each other, meaning if I take power and I add beta, I will get 1. I'll show you why here in just a second on our table. If I take power and I add beta, I get 1. So let me ask you guys this question. Mathematically speaking, what does power equal? Mathematically speaking, it's 1 minus beta. Mathematically speaking, what does beta equal? 1 minus power. Very good. Cool?
Say it again.
Power plus beta equals 1.
Okay.
So that means power is 1 minus beta,
Okay.
and beta is 1 minus power. Think about just subtracting to the other side.
Okay.
Okay. All right, cool. So let's look at this table. Remember this table from last time? I don't remember when we did it, but our null hypothesis is true or our alternative is true. That is not saying that I'm accepting the null hypothesis, but let's just be real. In actuality, you either are going to have a correct null hypothesis or a correct alternative, but we don't ever make that decision because we're basing our decisions on our sample, and so we are making a decision to either reject the null hypothesis or fail to reject the null hypothesis. So we did this either earlier this week or last week, I don't remember, but if we reject a null hypothesis that is actually true, what have we done? That's our type 1 error.
Is this not the same thing?
This is exactly the same thing. We're going to add one thing to it, though. The probability of this type 1 error is alpha. The probability of this type 1 error is alpha. If I reject the null hypothesis in favor of a true alternative, what have we done? We have done a good job, and this is exactly power. This is where power is. If I correctly reject the null hypothesis, that's power right there. All right, if I do not reject the null hypothesis, I fail to reject it, and it was true, and I didn't reject it, what happened? I did good. I did good. Now, there's no probability of, there's no word here. Okay, so don't worry about that. And then the last square here, I failed to reject the null hypothesis when the alternative was true. That's our type 2 error. And we just said the probability of a type 2 is equal to beta. So here is why power and beta add up to 1, right here. When you have an alternative hypothesis that is the true thing, you're going to do one of two things. You're either going to reject the null hypothesis in favor of that true alternative, or you're going to mess up and not reject your null hypothesis in favor of that true alternative. You only have one of two options there. That's it. When somebody is on trial and they are guilty, only one of two things is going to happen. They're either going to get proven guilty, or they're going to be proven not guilty incorrectly. That's the only two options.
Proven not guilty incorrect.
Correct. So
they are guilty.
correct.
Okay.
Yes. So that is why these add up to 1. So again, power plus beta equals 1. I can only make one of those two decisions when my alternative is true. I'm either going to reject the null and take that alternative, that's true, or I'm going to fail to reject the null and not take the alternative, and that would be a bad decision. Okay, so power, important. Power is important, and sometimes I want to make sure that I am getting it right. Sometimes the right decision is the most important one to make, and so I'm going to want to increase my power. This is the probability of putting a guilty person in jail. So let's say the death penalty's on the line. Don't you think I want to get it right? I probably want to get it right. That's why when death penalty cases are on the line, you have to really, really, really prove your case. It has to be beyond any shadow of any doubt that you believe that this person is guilty. So sometimes we want to increase power. So to increase power, we can do a couple of different things. The first thing we can do is we can increase our sample size. When we increase our sample size, we decrease the chance that we're going to mess up because we have really good representation from the population. So when we increase our sample size, we decrease the chance of messing up and powers the probability that we don't mess up. We can also increase the significance level. Now, hang on a second. What is the significance level? That's just alpha. So how does that work? Alpha is the probability of a type 1 error. If my type 1 error probability goes up, type 2 error goes down. And the probability of a type 2 error is equal to beta. So if alpha goes up, beta goes down. Now, if beta goes down, what's going to happen to power, which is the complement of beta? It's going to go up. So if beta goes up, beta goes down, my bad. If beta goes down, power goes up. Now this is like one of those SAT analogy things right here. If alpha goes up, beta goes down. If beta goes down, power goes up. So what happens to power when alpha goes up? It goes up as well. So that is why when I increase my significance level, I'm increasing my power as well. So here's kind of to summarize all of this. Alpha, the sample size, and power move in same direction. Beta moves opposite. Have any of you ever had a beta fish? Can you put them with other fish? Nope, they have to stay by themselves. So beta is by itself. It moves by itself in an opposite direction of this little fish, which is not really a fish. It's not a fish. Okay. Okay, cool. Let's do an example, guys. ADHD. Anybody heard of ADHD? The Centers for Disease Control and Prevention claims that 11% of American children aged 4 to 17 have attention deficit hyperactivity disorder. A company claims that it has developed a new vitamin tablet that will lower a child's risk of developing ADHD. Researchers will administer the vitamin tablet to 200 volunteer children under the age of 4 with parental consent. The subjects will be tracked through childhood, and the researchers will record the proportion of the subjects who develop ADHD. The researchers will perform a test at alpha equals 0.05 significance level. The null hypothesis is that the true proportion is 11%. Shh. The null hypothesis is that the true proportion is going to stay 11%, but their hope is that the vitamin is going to decrease the proportion under 11%. P is the true proportion of all children like those in the study who would develop ADHD when given the new vitamin tablet. The new vitamin tablet is expensive to produce, so we want to make sure we are really convinced that it's going to reduce the risk of ADHD. The power of the test to detect that, this should say P, you guys. That should not be another alpha. That should be a P. That P equals 0.05 is 0.937. Now, let me explain to you guys what that last little statement says. Basically, what we have is we have a distribution that is on 11%. We have a null hypothesis that's at 11%. This is the proportion of kids that get ADHD. What we're saying by this power statement right here is that if the actual proportion after taking the vitamin goes all the way down to 5%, then we have a 93.7% chance of proving that. That's what that means. The null hypothesis is that the true proportion is 11%. That's what has always happened with the ADHD. We've had 11% of the kids are having ADHD. We're giving them this new vitamin to prove that the true proportion has decreased. To prove that P is all the way down to 0.05, we would have a 93.7% chance of proving that. So, the chance of proving that P decreased from 0.11 to 0.05 is 0.937. That's our chance of proving that this vitamin decreased our ADHD from 11% all the way down to 5%. Is that a pretty good chance? That's a pretty good chance. I mean, 93.7% chance?
That's a great chance.
That's a pretty good chance.
That's a great chance.
If that's the case, then would I want to go ahead and produce this really expensive vitamin? What do you think? If that's the chance that I've proven this to be true, would I want to do this expensive vitamin? Yeah? Yeah? Okay. Okay.
Let's do it.
Cool, let's do it. I'm with you. All right, what is the probability of a type 1 and type 2 error? Y'all can find this. Ready, go. You can do this. It's easy. Probability type 1, type 2 error.
I know.
You don't need a calculator for this, man.
Okay.
All right, what's our probability of a type 1 error?
0.05
How'd you get that?
alpha.
That's just alpha, right? So the probability of type 1 error is just alpha, which is 0.05. Easy. Okay, cool. Type 2 error. What's the probability of type 2 error?
0.063.
How in the world, Grace, did you get 0.063? I didn't see 0.063 anywhere in the problem.
I didn't
It's 1 minus beta, which is
Nice. So Grace remembered that just a minute ago we found out that beta, which is the probability of type 2 error, is 1 minus power. And so we take 1, we subtract the power, 0.937, and we get 0.063. Nice. Good job. Okay, what happens if we use alpha of 0.1 instead of alpha of 0.05? What's going to happen to power? Increase or decrease? Increase, increase. I hear that twice. Going 3 times.
Increase.
Increase. Are we sold?
Sold.
Sold. All right. If alpha goes up, power goes up. Remember, those move in the same direction? So power would increase. Is this a good thing?
Yes.
Why? Why is this a good thing?
It means that you're correctly rejecting.
I am correctly rejecting the null hypothesis. You're right. You're right. All right, cool.
I'm just reading notes.
It's fine. You're amazing. All right. This one's a little bit tricky right here. If the true proportion of P If the vitamin changes P to 0.08 instead of 0.05, what happens to power then? So, think about it this way. We've got our true proportion is currently at 11%. If I get the true proportion to decrease all the way down to 5%, and I can prove this, it's going to be pretty easy to see a big difference here, right? So like if I take a sample, I should be able to pretty easily tell if it's over at 11 or over here at 5, because there's a pretty big difference there. But if I'm here at 8%, then it's going to be a little bit harder to tell if there's really a difference because of the vitamin or if it was just sampling variability. So it's going to be a little bit harder to prove that I have actual change. So what does that mean about power? Will it be easier to prove the alternative or harder to prove?
Harder.
Very good. All right, so power would decrease because 0.08 is closer to the claimed value. .08 is closer to the claim value, so it's harder to prove that there's a difference. It's kind of like if a crime happens in the downtown McKinney area, and you are over at McKinney High School when it happens. You're closer to the crime and might be part of the suspect pool. But if you're all the way over in Frisco, it's pretty hard to prove that you were a part of that crime. Okay?
Depends how long ago the crime happened.
This is a good point.
And that's
Whoops.
with any case.
My
A
bad.
good detective would
Yeah, well.
find out.
What if we use n of 500 instead of n equals 200? What would happen to the power of the test? Yep. So when n increases, power increases because we have better data to prove the alternative hypothesis. We have better data, more data, better data to prove the alternative hypothesis.
Wow, that's
Mm-hmm.